Welcome to our video on the derivatives of inverse functions. So we're talking about f of x, or f of x is invertible and it's differentiable, which means that f of x will have an inverse function and also a derivative function. F raised to the negative 1 of x means the function f of x has a inverse function called f to the negative 1 of x. So it's not an exponent, it's just a notation signifying the inverse function of f of x. We're going to try to simplify that notation a little bit, and we're going to call the inverse function g of x. Okay, so the inverse function g of x is also differentiable. All right, we also know that if AB is a point on the graph of f of x, then BA must be on the graph of the inverse function g of x, where f of x and g of x are inverses of one another. All right, and you may recall that from when we studied inverse functions in Algebra 2 and Pre-Calculus. Now let's talk about slope. If P over Q is the slope of the tangent line to f of x at the point AB, then the reciprocal Q over P is the slope of the tangent line to the inverse function g of x at the point BA, which is the flipped of the point AB. So the slopes are reciprocals of inverse functions at corresponding points. Now let's explain these concepts using a graph. So we've said that g of x represents the inverse function of f. The point AB will lie on f. So in our picture here, A is 10, B is 4, and the point BA will lie on G. So those two are going to be flipped. So now B is first, A is second. All right, so this formula here, what I'm calling Formula 1, talks about the slopes of the tangent lines at those 2 points being inverses of one another. So notice on the left-hand side of this formula, we're talking about evaluating the slope of the tangent line when x is 10. In our case, A is 10. And then on the right-hand side of the formula, we're talking about evaluating the slope of the tangent line to the graph of g of x, where now x is your b value. All right, so this is what we're calling Formula 1. So let's put some numbers in that formula and see if we can understand that. So if I'm looking at f prime of 10, that means I want the slope of the tangent line to the function f at x is equal to 10. So the slope of the tangent line here, according to my picture, is 1 over 3. 1 over 3. Now right here, this is the right-hand side of Formula 1. This says I've got 1 over the slope of the tangent line to the g function at 4, when x is 4. So I'm over here, the g function. Now x is 4 because a, b are inverted. The slope over here, the tangent line, is 3 over 1. 3 over 1. So now if I say 1 times, flip and multiply, I can verify that it is indeed 1/3. So this is just a graph that helps us to internalize what we're talking about with the slopes being reciprocals of one another. So I'm going to highlight this formula, which we're going to use in our problems. Example 1 says, given the function f of x is equal to 5x cubed plus 4, part A, find f prime of x at x is equal to 2. So this part is just taking the first derivative of f. So f prime of x is going to be 3 times 5, drop the power down by 1, plus the derivative of 4 is 0, so 15x squared. evaluated at 2, f prime of 2 is 15 times 2 squared, which is 15 times 4. So f prime of 2 is equal to 60. So we're talking about the point 2 f of 2. So this would be my A, B. So what I found here is f prime of A is equal to 60. All right. Second, part B, it says find an equation for y is equal to the inverse function of f. So we said we were going to call that g of x. And we're doing that just to simplify having to use that -1 in the power position, which can get in the way. So we're going to do this the algebra 2 way that you might recall, where I have y in my original equation is equal to 5x cubed plus 4, and I can switch x and y and solve for y. So I've got 5y cubed is equal to x minus 4, or y cubed is equal to x minus 4 divided by 5, or y is equal to the cube root of x minus 4 divided by 5. And then I'll call that g of x, my inverse function of the function f of x is the cube root of x minus 4 divided by 5. Part C says, find f inverse prime of x, and this is where we're going to simplify the notation and call this g prime of x at x is equal to f of 2, so we really want g prime evaluated at f of 2. All right, so there's two ways we can envision doing this. One is the long way and one is the short way, which utilizes Formula 1. So the long way would be to figure out what f of 2 is, which we haven't bothered to do yet, and that we would do by putting 2 into the original function, and then going ahead and taking the derivative of g, which is this here, and then substituting f of 2 into the derivative of g of x. Right? That's the long way of doing it. Otherwise, the short way would be to utilize Formula 1. So Formula 1 says f prime of A is equal to the reciprocal of g prime of B, or we could write it the other way by flipping both sides around, 1 over f prime of A, and I could flip the right-hand side, which would put the 1 down at the bottom, would be g prime of B. Notice that what we're interested in here is g prime of B, because here B is f of 2 when A is 2. So we're interested in g prime of B. If we want g prime of B and we know f prime of A, it's just a question of flipping it and taking the reciprocal. But don't we know f prime of A? Because that's what we figured out here. So f prime of A is equal to 60. So that means g prime of f of 2 is equal to 1 over f prime of 2, which is 1 over 60. So we just had to flip over f prime of 2, and we have g prime of f of 2. So that's the shorter way of doing it, and that's what Formula 1 does for you, and that's the understanding that we're trying to develop here when we're talking about the relationship between the tangent lines at corresponding points on functions that are inverses of each other. Example 2 says, given the function 6 over 5 plus x squared, part A, find the slope of the tangent line to the inverse function f inverse of x at this point 3, 1. All right, so if 3, 1 is on the graph of f inverse of x, we're going to call this g of x like we did the last time. So if 3, 1 is on the graph of g of x, then 1, 3 must be on the graph of f of x. So A, B, B, A. All right, so we know that about the point. So we can do what we did last time in example 1 and use formula 1. Since we're given the f function, we can find f prime of A and then take the reciprocal of that, and that'll give us g prime of B. All right, so we're interested in finding g prime of B. G prime of B, that's g prime of 3. That's what we want. The slope of the tangent line to the inverse function, f inverse of x, which is g of x at the point 3, 1. So g prime of 3 is what we're after. So formula 1 says g prime of B is the reciprocal of f prime of A. All right, so we need to find f prime of A. So that's our job. So f prime of x, using the quotient rule, is the bottom times the derivative of the top, which is 0, minus the top, times the derivative of the bottom, which is 2x, divided by the bottom squared, which is equal to negative 12x over 5 plus x squared, squared. So if we want g prime of 3, let's erase this question mark here. We want 1 over f prime of A, where A is 1. So we need to evaluate f prime when x is 1. So it'd be negative 12 times 1 divided by 5 plus 1 squared, squared. Negative 12 divided by 36, that's negative 1 over 3. So f prime of 1 is equal to negative 1 over 3. So that means g prime of 3 is equal to negative 3 over 1, which is just negative 3. And once again, we didn't have to find the function g prime of x and evaluate it 3. We're just able to use formula 1 and avoid that work. B says find an equation for the tangent line to the inverse function at the point 3, 1. All right, so g prime of 3 is equal to the slope of the tangent line at that point 3, 1, and we're saying that's negative 3. So using the point slope formula, y minus 1 is going to equal to negative 3 times x minus 3, and we should always simplify this. So I'm just going to simplify this, and I'll have y is equal to negative 3x plus 10. And what we have here is an equation for the slope of the tangent line to the inverse function at the point BA 3, 1. And we found that slope using formula 1 and not actually having to take the derivative of the inverse function. The only thing we needed to find out was the derivative of the original function f of x. So example 3 says for the function f of x given, we have a domain restriction, x must be greater than or equal to 5, and we're interested in finding f inverse prime of 4. That's the slope of the inverse function of f, and we are calling that g prime of 4, evaluated at 4. So the slope of g when x is equal to 4. So we're given b this time. B is 4, and we're not given a. So we've got the point A 4. All right. So that means f of A is equal to 4, but we don't know A. So if we're asked to find G prime of B, and we want to use formula 1, G prime of B is reciprocal of F prime of A. So since we know the function f, we can easily find f prime, and if we could find A, we would evaluate f prime at A, and we'd have G prime of B. So that's going to be our strategy. So we're going to back out A, knowing that f of A is equal to 4. So let's start with that. F of A is equal to 4. So if I put A into my function, A squared minus A plus 3, that must equal 4. So I can solve this for A, because it looks like a quadratic. All right, so let's move the 4 over there, set it up with a 0 on the right-hand side, so we can use quadratic formula. All right, so we're going to use, I'm going to abbreviate quadratic formula since it's not factorable. All right, so I've got the coefficients 1, negative 1, and negative 1. So solving for A here, so I've got negative 1 plus or minus the square root of negative 1 squared minus 4 times 1 times negative 1 divided by 2 times 1. So just simplifying this, I've got 1 plus 4, that's 5 under the radical. All right, so that's 1 plus root 5 divided by 2, and 1 minus root 5 divided by 2. So those two numbers, if I plug them into my calculator, are 1, let me just write them down. So those are my two numbers. Now this is where the domain restriction comes in. We're restricting ourselves to x being greater than or equal to 0.5. So this is the A value which qualifies. So right here, this one's our A value. All right, so now we know A. So the only other thing we need is f prime of x, and we'll substitute that value, and we'll have f prime of A. All right, so now let's differentiate f of x. So f prime of x is going to be using the power rule on the original function f of x, 2x minus 1. F prime of 1.6180339 equals 2 times that number minus 1. So f prime of A, let me just write A, is equal to this number right there. So now, finally, G prime of B is just going to be the reciprocal of that number. And if I run that through my calculator, I'll have what I was after, which is G prime of B. Well, B was 4, and that number is this final answer here. All right, so this is the slope of the tangent line of the inverse function G evaluated at 4. So there's a lot of vocabulary running around here. It's easy to trip over. So that answers our question. That answers our original question was we wanted to find G prime of 4. All right, so we did it. G prime of 4, and we did that by backing out the A value, finding the derivative of the f function, substituting the A value into the f prime function, and taking the reciprocal of that, and that gave us the slope of the G prime function, the slope of the G function evaluated at 4. All right, so a lot of ways to trip over these vocabulary words here. All right, so the next thing we talk about is the derivatives of inverse trig functions. Okay, so more talk about inverse functions. So we have these 6 formulas here for each of the 6 trig functions. And so we're just going to utilize these functions that are already derived, and we're not going to go too much into the derivation except for the first one, the derivative of the inverse sine function. So let's go ahead and do that first. So what I'm going to show you here is how we get this formula here and how it's related to right triangle trigonometry. So the first thing I'm going to say, let's just write f of x is equal to the inverse sine, which means the angle whose sine is x. And I'm going to replace f of x with y. So y is the angle whose sine is x. All right, so now I'm going to take the sine of both sides. I'm doing what I do to the left, I'm going to do to the right. Sine of the inverse sine of x. All right, so these two right here are inverses of each other. So that means we can cancel them out. The sine of y is equal to x. So if the sine of y is equal to x, y is an angle. So if this is my angle y, then the sine we know is opposite over hypotenuse. According to this little triangle right here, that corresponds to this statement. The sine of the angle y is x over 1, x over 1. I can find this missing side here using Pythagorean theorem. So 1 squared minus x squared square root is equal to square root of 1 minus x squared. So that's my missing side. That's my other leg of that right triangle using Pythagorean theorem. And the other thing I can say about this right triangle, one other thing I could say now, is that the cosine of the angle y is equal to adjacent over hypotenuse, which is 1 minus x squared over 1. So we know the cosine and the sine of y. All right, so now, knowing that, if I start with sine of y is equal to x, that's this here, and I take the derivative of both sides, what you do to the left, you do to the right to keep your equation balanced. The derivative of the sine is the cosine. Using the chain rule, dy dx, take the derivative of the y with respect to x. This is the chain rule. On the right-hand side, the derivative of x is just 1. So if I solve for dy dx, I get 1 over the cosine of y. That's the same thing as knowing cosine of y is 1 over the square root of 1 minus x squared. But y was originally inverse sine of x. So this is the derivative, d by dx, the derivative with respect to x of the sine, the inverse sine of x. And that's equal to 1 over the square root of 1 minus x squared. And that's our formula. So this is how these are derived from right triangle trig in combination with what we know about the derivative of trig functions so far. So I'm not going to go into any more of them than this one, just so that you can kind of understand why we've got this structure here with the square roots and stuff. It all has to do with right triangle trigonometry. Okay, so now we're just going to use those formulas. We're not going to bother deriving any more of them. And so here in this particular example, we're going to use the chain rule to find the derivative of this function here involving an inverse cosine function. All right, so first off, I need the formula for the derivative of the inverse cosine. So if I go back to this page of formulas, we're talking about using this formula here. So here's my formula. Now, what you're going to notice here is that this part right here, this x is a lot more, well, not a lot more, but it's more complicated in my function f of x that I'm given here. So this part there is not a plain x, it's a 3x squared. So the way that you handle that is using the chain rule. So f prime of x in our case is equal to 2, the constant out front. Now I substitute into my derivative formula 1 minus, but instead of an x there, I have a 3x squared. And therefore, I've got to use the chain rule. I've got to multiply by the derivative of whatever that part is there, which is 3x squared in my case. All right, so now let's simplify this. So I can just put this 2 times negative 1 in the numerator. Square root of 1 minus 3 squared is 9, x squared is x4. And then the derivative of 3x squared is just 6x. So I can put that up on the top here. So I end up getting negative 12x over the square root of 1 minus 9x to the 4th. All right, so we have to use the chain rule when we have something in there that's not just an x, non-x I called it. Something more complicated than just an x right there. Right, here's another example. So this time we're going to use the formula for the derivative of the inverse sine function. So there's my formula, and I've got right here something that I'm going to have to use the chain rule for, because it's not just a plain x. All right, so now, taking the derivative of f of x, f prime of x, I've got the constant 3. Now the derivative of the inverse sine is 1 over the square root of 1 minus. So instead of just an x, I put 6x to the 7th squared. And then I have to multiply by the derivative of 6x to the 7th using the chain rule. So that's equal to 3 on the top. 1 minus, that'd be 36x to the 14th if I square that. And this would be 42x to the 6th, like that. So I need 3 times 42, so that's 126 times x to the 6th in the numerator. In the denominator, 1 minus 36x to the 14th. So this is your f prime of x using the formula for differentiating the inverse sine of x and the chain rule combined. Example 7 says, use the chain rule to find the derivative of the inverse tangent function. So once again, I can see that I have something in here that's going to require the chain rule because it's not just a plain x. So the formula for the derivative of the inverse tangent function is 1 over 1 plus x squared. So f prime of x is equal to the constant 3 times the derivative of the inverse tangent, 1 over 1 plus. So I have to put cosine of 4x where x goes in the formula. I can see that I'm going to then have to multiply by the derivative with respect to x of cosine of 4x. So that's going to be 3 in the numerator, 1 plus the cosine squared of 4x in the denominator times the derivative of the cosine, which is the negative sine of 4x, times the derivative of 4x now, because the sine has something other than just an x right here. So we have 3 over 1 plus the cosine squared of 4x times the negative sine of 4x times 4. All right, so now in the numerator we can put 3 times 4 as well as the negative. That's negative 12 times the sine of 4x. That would be my numerator. And then my denominator is 1 plus the cosine squared of 4x. All right, so that's your derivative. And I had to use the chain rule again because I didn't have just a plain x there in the argument. Example 8 says use the chain rule to find the derivative of this one. And once again, I've got an argument that is not just a plain x, it's some kind of other composite function. So I'm using the formula for the derivative of the inverse tangent again, and there's the formula. So the derivative of f constant is 3. So in the formula I've got 1 plus, instead of an x, I've got 6 sine of 2x squared. And then times that, using the chain rule, times the derivative of 6 times the sine of 2x. So now, the next line down, I've got 3 in the numerator. 1 plus 6 times 6, that's 36. Then sine squared of 2x. All right, then the derivative of 6 sine of 2x is 6 times the cosine of 2x, and then times the derivative of 2x, which is just 2, using the chain rule. All right, so now in the numerator I've got 3 times 6 times 2, that's 36. 18 times 2, that's 36. Cosine of 2x, and then in the denominator 1 plus 36 times the sine squared of 2x. Right, so that's f prime of x. Using formula for the inverse tan function, the derivative of the inverse tan function, as well as the chain rule. All right, so that's applying these formulas. Last problem I want to do is an application type problem. So this kind of a picture could apply to different wordings of different scenarios. So this is more of like a generic problem. So it says, in the triangle shown, side AC is x. So I'm going to write on x on AC. Side BC is 30 feet. Down here, 30 feet. And theta is the angle ABC. ABC. So this is my angle theta. All right. Part A says write an equation for theta in terms of x. So theta is the inverse tangent, opposite is x, adjacent is 30. Theta is the inverse tangent of x over 30. All right, that's my equation. Part B says write an equation for the rate of change of theta as x is changing. So the rate of change of theta with respect to x. So we can call that theta prime, or d theta dx, the change in theta as x changes with respect to x. All right, rate of change of theta with respect to x. So that means I've got to differentiate inverse tangent of x over 30. So I can use my formula for the derivative of the inverse tangent function. So there's my formula. So that means I've got 1 over 1 plus, so my x is, in this case, replaced by x over 30 squared. But that in itself is a function, so using the chain rule, the derivative with respect to x of x over 30. All right, so that means theta prime is equal to the derivative with respect to x of x over 30 is just 1 over 30, which is the coefficient of x. Let's put that on top. 1 over 30 over 1 plus x over 30 squared. Let's just leave it like that rather than square the 30. All right, so that's theta prime. Now C says, what is the instantaneous rate of change when the distance from A to B is 55 feet? A to B is 55 feet. Give units. All right, so if that distance is 55, then that's going to give me, let's write that down, if AB is equal to 55, then x is going to be a particular instantaneous value. And that will be, according to Pythagorean theorem, 55 squared, hypotenuse squared, minus 30 squared, and the square root of that number. That's going to be my x. All right, so if I plug that into the calculator, at this instant in time, when AB is 55, x is this number here that I got by plugging that into the calculator. All right? So we want to evaluate what the instantaneous rate of change is at that x value. So basically that means I'm going to substitute x into theta prime. So I've got this 1 over 30 is my numerator, and I've got 1 plus 46.0977229, scoot it up a little, over 30 quantity squared. All right, so I'm going to type that into the calculator, and I'm going to get, so sometimes if you're noticing that you're having a little bit of difficulty typing long things into the calculator, do it with a numerator and the denominator as I'm demonstrating here, so that you're sure you're not messing that up, how you're typing it into the calculator. So if I divide those two out, I'm getting theta prime at that x value in question is this amount here. So now it asked for units. Now let's think about the change in an angle with respect to the change in a side length. What kind of units would that be? Well, angles are in radians. So think about it in terms of what you know. Velocity is change in distance over time, like feet over time. All right? But if we're talking about change in angle, we're talking about changing radians, and not with time in this problem, with another distance, which is given to us in feet. So this is radians per feet. The angle is changing as the side is changing. So units of angle divided by units of side length. All right, so this is our answer here. our angle is changing by that amount as your side length is changing by as you're at your instant when the AB side is 55 feet. So going back and highlighting our answers, A, that's our equation for theta in terms of x. B, that's the derivative of our equation for theta. And C, this is the rate of change of theta as at the instant in time when x is given to us in terms of the hypotenuse being 55. We had to back out the x length and substitute that x value into our theta prime equation. All right, so that wraps up our example problems here having to do with derivatives of inverse functions. You should be ready to try the homework problems now.